Hello, my dear students. In this class, I am going to discuss defects in crystal or imperfection in crystal. So, before going to that, let us go through these images. Carefully observe the crystal lattice and lattice points, the position of the lattice points, and the arrangement. So you observe all these things in a given crystal and you observe here. So in a crystalline lattice, some atoms are vibrating, and along with that, so this vibration leads to change in their position, and this is another crystal lattice in which, so please observe the shifting of a red color atoms. So red color atoms, so line by line, so there is a shifting, the position is changing due to some external force, and you observe here. So in this, so one red color atoms is changing its position. It is going to occupy the free space which is present in the crystal lattice. The position is changing and it is randomly moving within the crystal lattice. So these are called as imperfection. So why we are using imperfection or defects? Dear students, so we know that what's the crystal? Crystal is famous for its systematic arrangement. The systematic arrangement in a three-dimensional manner, it gives a standard regular geometry. For this we are called as crystal. That means there is a perfection in their arrangement. But is there any deviation, departure, or other than this perfection either in the arrangements of constituent particle and change in position, shifting of position takes place in a crystal lattice? So this situation is called as defects or imperfection in crystalline solids. So the crystal or perfect arrangement when it is at absolute degree temperature. That means the 0 Kelvin is called as absolute temperature. At this temperature, they possess perfect arrangement of constituent particle. But the environment which is around the crystalline substance is not always same. Something temperature varies, pressure varies, something we are going to apply the external force. So you know that the crystals are brittle in nature. You know the reason behind the brittleness of a crystal. That means when we apply the force on the crystal, at that moment what happens? The interionic distance decreases. So the interionic, if you apply the force on this crystal, the interionic size decreases. So if interionic, that means if similar charges comes nearer, so at that moment a repulsion takes place. This repulsion leads to a breaking of a crystal. So this is called as brittleness. So there are various reasons in which defects, imperfection takes place. That is, so there is a change in temperature, change in pressure, or applying force on the crystal. So the various environmental changes are responsible for changes the ideal arrangement, the perfect arrangement in a crystalline solid. So this is called as imperfection at crystal. So this imperfection can take place, you just look at this example. This defects or imperfection can takes place in different ways. So either, for example, this is a sodium chloride crystal. For this sodium chloride crystal, a strontium may enter into a crystalline lattice. That is impurity. Okay. Okay, the crystal get impure. Strontium may enter. Sometimes so sodium is move from the system. So vacancy can be created, or sometimes so the entire this row get displaced. So there are various possibilities. So the change, based on the defects, nature of defect, the crystalline defects are classified into two types. One is point defect and line defect. So point defect means the defect takes place either, so an atom is get replaced by another atom, or an atom occupy interstitial position. This is called as point defect. That is, one atom is undergo a changing. Line defect means entire row is undergo defects. So this is called as line defects. So again, point defects are further classified into three types. One is impurity defect, stoichiometric defect, and non-stoichiometric defect. So dear students, so based on the nature of defect, the mode of defect takes place in a crystalline substance, we are classify the crystalline defects into two major category. One is point defect and second one is line defect. Point defect further classified into three types. One is impurity defect, stoichiometric defect, non-stoichiometric defect. So then line defects. So as I said, line defect is nothing but the irregularity or deviation from an ideal arrangement of a constituent particle in an entire row of a lattice is known as line defects. So let us see one by one. Stoichiometric defect. You know stoichiometric composition. For example, if you take sodium chloride, the stoichiometric composition in case of sodium chloride compound is 1:1. So this is a stoichiometry. Okay, suppose in a single crystal, suppose there are 1 lakh sodium atom is present, exactly 1 lakh chloride ions are present in that crystal. That means stoichiometry. There is a suitable amount of ratio which is exist in a crystal. So this is called as stoichiometry. Stoichiometric defect means the crystal undergo defect, but the stoichiometric ratio does not alter. So this is called as stoichiometric defect. So for example, let us consider this sodium chloride crystal. In this sodium chloride crystal, maybe one sodium. So the stoichiometry of sodium is 1:1. Suppose if two sodium atoms are missing from this crystal lattice at the moment, the ratio is no longer 1:1. Instead of that, so 1:2, so 0.8, 0.9, 0.95, like that, 0.98. So the ratio is changed. So here the stoichiometry is altered. So once again, dear student, suppose if both the cations are missing from the crystalline lattice at that moment, so chloride atoms are more and sodium atoms are less. So at that moment the ratio is changed. You will get a fraction. In case suppose one anion and one cation is missing, nothing will happen, and at that moment also the ratio of sodium and chloride is 1:1. So this is called as stoichiometric defect. That means the defect takes place in which the number of cations or equal number of ions, cations and anions, are missing, and this type of defect obeys law of constant composition. That is, the chemical compound always contains same number of element, same composition by weight. So as I said, this stoichiometric defect is classified into four categories. One is vacancy defect, interstitial defect, Schottky defect, and Frenkel defect. Let us see one by one. So first one is vacancy defect. Vacancy, as the name itself indicates, that some ions are vacant. So see here, Actually, this is a vacant position. Some ions are left the crystalline lattice, so due to some environmental effect, due to some thermal effect, some ions are missing in the crystal. So as a result, a vacancy is created, so inside the crystalline lattice. So this is called as vacancy defect. And so as a result of vacancy defect, so the density is decreases, because so as the two ions left their position, so volume will be more. So if we know that, so density is nothing but mass divided by volume. So here mass is decreases, that means if two atoms are missing from the unit cell, mass is decreases. As a result, the density also decreases. So this is called as vacancy defect. Next one is interstitial defect. So in this defect, no ions are missing. Instead of that, you please observe this unit cell, this crystalline lattice. So there is interstitial position, that is, so let us consider a room. In a room, if I allow you to fill the ball, for example cricket ball, it is not possible to occupy the entire volume by the number of cricket ball. Some vacant space which is present, so between the balls. So like that, in an unit cell, in a crystalline lattice, even though atoms are closely packed, some vacant region, some vacant space is present. This vacant space is called as interstitial region. Okay, so during defect what happened? Some atom, instead of their original position, they are going to occupy the interstitial region. Okay, they are come here, they are occupy the interstitial positions. So this defect is called as interstitial defect. So in this defect, density is increases. That means already some crystal lattice is there. So to the crystal lattice, to the vacant position, some extra atoms are come and enter. So this is called as interstitial defect. So here mass of a crystalline lattice is increases, volume remains same. So that's why the density of the crystal lattice is increases in case of vacancy defect. Next, Schottky defect. This is a third type of stoichiometric defect. Schottky defect means, let us consider this crystalline lattice. So in this you observe here, so this crystalline lattice of a crystal which is made by a constituent, so A plus cation, B minus anion. You observe the figure here, B minus 1B minus 1B minus, totally 2B minus, and so 1A plus, and this is another A plus, so 2A plus, that is 2 equal number of 2 cations and 2 anions are missing. That means the stoichiometric defect takes place in an ionic crystal. So in this what happens? Equal number of cations and anions are missing. So as a result, they are going to create a pair of holes. I think you are know the concept of holes which we are studied while discussing semiconductor. So equal number of cations and anions are missing. So as a result, the density of a crystal is decreases due to the loss of mass, and covalent character also decreases. And this type of defect usually observed in strongly ionic compound, and this type of defect observed when both the size of both cations and anions are equal. At that moment we are going to observe this type of defect. So this is called as Schottky defect. That means in Schottky defect, both anions or cations are missing. As a result, density is decreases, their covalent character in a crystal is decreases, their coordination number also decreases, and this type of defect takes place in a crystal in which the size of cations is equal to size of anion. So next class I am going to continuing the Frankel defect.